June 8, 8 o'clock. I'm redoing the test today. The inverter is purely running on a battery. So turn on the AC. It's on. Let's see. Input 60 hertz, output 60 hertz. Battery at 27.7. Battery 3 amps. That's standby. Input is 250 volts. So I'm gonna turn off AC input. Unplug it. So now it's purely on 220. There's no load because I haven't switched the power. So I have actually, I want to do this quick. I don't have time for like, I don't know, 5 hours. So 5 fan, and now I'm going to turn the AC to the house. Power to the house is active. Now with this aircon and things powered up, so load is at 720 watts. Basically VA and watts are about the same. The power factor correction is not so big. Load is 19%, 19, 20. So no solar. So everything is running on a battery. So 26 dropped from 1 volt. It would have been nice if it actually measures the current draw from the battery. However, this is all right. So let's do some calculation. Okay, so these are the information that I have. So 220 output, 720 watts is being used by the house. The battery capacity is 24 volts times 100 amp hour gives you 2400 watt hour. Now divide 2400 by 720 gives you basically, that cancels out. You got hour left. So 3.3 hour or 3 hours 18 minutes. The inverter efficiency is 99.5% efficient. I actually don't believe that. The conversion from battery, this thing, switching the battery to 12 to 20, having like almost 100% efficiency, it's the technology has to be fairly good. Anyway, we'll see. I mean, is that really, in fact, I don't even know the quality of the battery. However, regardless of all of that, will we meet 3.3 hours? It's started at 8 o'clock. 8 o'clock started at 8 a.m. 8 a.m. So add 3, so that would be at 11 o'clock. Should be, let's see, 8 to 9, that's 1, 9 to 10, yeah. Should be done by 11 o'clock. So, is that real? So, we'll see if it's real. Now it should be at steady state. Let's see. So the battery immediately drops to 25.7 volts. So 750. Okay, that's the steady state, 750. I mean, nominal, let's just call it that. So 720 is good enough. However, let's do a recalculation of 2400 divided by 750. how many hours is that? Let me just do a quick calculation. So with 750, I mean it improves by 6 minutes. So anyway, will it meet 3 hours with fully charged battery? The curve of this battery is basically so 27 volts, and then immediately went to 25 volts. I mean nominal is what you call 24 volts, okay, nominal. So the thing I don't like about lithium in particular, especially with BMS, is the sudden cut of power, abrupt. So if you don't have the capacity to run a household, the power to the house terminates abruptly. And so sometimes if you don't know what you're looking for, what you call cut, or cut off abruptly. Really not good. So what is that? If you do things properly, this is what you call what is the word I'm looking for? Soft drop, and the inverter should provide a warning, but because of the BMS, you don't have that soft cut. So sometimes it's better to have multiple batteries where it meets your let's say criteria, and I think sometimes it's better to have more intelligence into the system where there's a bit of a warning before things terminate abruptly. So but that's the way it is. Maybe someday I'll build a system that would do that. So here it's steady at 25.7, which is 25.7. I think it's 7. The so when we talk about nominal, there's a flat voltage where this thing, if you zoom in, it's actually slowly drop over time. It's not like flat. It's not like flat. It just slowly drift to that abrupt cutoff. So to make calculation easy, when we say 24 volts battery, 24 volt nominal, so that you can calculate things like this, and you get an estimate of the battery capacity. So the question is, will I get 3 hours 12 minutes? So it's a question mark. Is this real? It's not real. 99.9% is not real. Well, how do you measure efficiency? Well, you gotta have special equipment, and I don't. But I don't trust that number. So 1 aircon, 5 fan, 1 fridge running, consuming this fully charged battery. So it's the whole house is basically running on battery, and it should last 3 hours. Would we reach 3 hours? We'll see. It'll be a good experiment. So I got things to do around the house, so I'm just gonna do that. The time now is 8:38, and the steady state is varying from 8:25 to 8:45. So let's just call it 830 nominal watts. So let's redo the calculation. So with the changing of steady state watt consumption, then the duration drops to 2 hour 53 minutes. So not only will the time drops, I mean talking hours, so initial calculation sort of drops also. So this was, for example, this was initial calculation was 3 hour 18 minutes. Now it's dropping to 2 hour 53 minutes. So as the power consumption increases in steady state, then this thing will drop. Now that's quite interesting. Let's see what the battery is. Battery is at 27, 26, 26. And the battery here 25.6, so 0.4 volts drop, but note that the steady state nominal is 25.6. So we'll see. The time now is 8:48, and there's something that typically happens when the aircon is running for a while. It started to draw more current, and so it changes the nominal energy use. As you can see, it's now running around 882 max, 870. Well, let's just call it 877. So I'll do a new calculation of 877 watts. So with this draw of 877 watts, recalculating the duration, it becomes 2 hour 44 minutes. So 2 hour 44 minutes. So basically, if a person integrates the energy use over time, basically integration is average of energy use over time, watt hour. You can then get a sense of what the house energy use is when using battery and inverter. Okay, so what does all that mean? Well, you can then calculate how many batteries you need. Let's say it was 100 amp hour. How many batteries do you need to run 24 hours? That sort of thing. So basically, for example, if you're just dealing with 3 hours, so or 2 hours, so 24 divided by 2, so 1 2 basically you need 12 of these to run 24 hour. Do you really need 2 of these? Actually, you don't. Do you really need 12 of these? No, you don't. What you need is more solar. So basically, what does that mean if you have more solar? So right now I have two solar. Okay, and it only gives you a certain amount of watts. Okay, now suppose you have, let's see, right now two 600 watts. Okay, will give you 1200 watt. Ideal, under ideal condition, but you don't actually get 1200 watt. So you say, well, okay, well, since I'm not getting full 1200 watt, then make it full. You know, let's say you have 4. Okay, so another 600. This is using during the day. Okay, so you have 2400 watt. Okay, 12 plus 12. Now you're during the day, the sun is like this. Okay, the watts, let's say the watts is 500, and then this is 2400, and this is 600. 500 again. So since you're only consuming, for example, I'm consuming, let's just make it 900. I'm consuming on the average 900 watts. Okay. Uh, so basically at this point where it's only 500, then it's taking from the battery. And then at some point, there's a switchover where now the solar can give the energy. So all of the energy goes to powering up the house, and charging, okay, slash charging. So now you have this house charging thing because you have 2400 watts. Some of it will go to powering up the house and a lot of it will go to charging the battery. At some point, you have what you call a changeover again. So now here it's taking most of the energy from the battery. So from here, okay, bat. From here, bat. Okay. So charging, and most of the energy is to charge. Some is diverted to powering up the house. So basically at some point, let's say here is house, here is charging. So that's the pie chart. So you gotta really smart about your capacity. I mean, yeah, you can have more battery. Okay, so okay, you have battery in parallel. Okay. Okay, so there, let's say 100 amp hour, 100 amp hour, 100 amp hour, and these are of course in parallel. So now you have 300 amp hour. Okay, so well, you say, well, what's 300 amp hour? So 24 times 300 amp hour. So let me just do a quick calculation. So okay, so you have three 100 amp hour, and they add up, so to 300 amp hour. These are of course 24 volt. Okay, so what does this mean? So 24 volt times 300 gives you 7200 watt hour. Okay, so 72 divided by 900 watts will give you 8 hour. So it's okay. Are you happy with 8 hours? Because each battery, like for example, they're really expensive. For 100 amp hour, I don't know, 12,000. With 12,000 you can buy panels. So you have to ask yourself, when do you really need to have battery? To me, you need most of the energy during the day. During the night, if you're okay with running a fan, then a fan will last you with this kind of capacity. Will last you a long time. So you have to kind of understand when do you really need the energy. To me, because it's so hot in the Philippines, I would be running the aircon. Right now I'm not running the aircon during the day because what for? I can always go outside. During the night, if the night is cool, you're not running the aircon, so the battery charge lasts a little bit more. To me, again, for me, during the day, go outside. During the night, run the aircon. I mean, you wanna minimize the amount of energy you use during the night. Okay, you can always run the fan. What else? Of course, fridge is always important. The other factor too is there's a rolling blackout in the Philippines, so you don't know when you're gonna get the rolling blackout. So you want to conserve your energy use or the battery capacity. Blackout When it's really hot, go outside. When you can bear it no more, run the aircon, that sort of thing. So during the day, really, add more solar capacity. But then that's just my opinion. I mean, you do have your own opinion. I'm wanting to help with when do you need more battery capacity versus when do you need more solar capacity. Um, yeah, I guess it's up to the individual to decide what is more important. For me, what is more important: rolling blackout, really hot day, uh, budget, uh, batteries double the cost of a two solar. Now, instead of 100 amp hour, you could put in 300 amp hour. Still, one single battery will give you 300 amp hour. You get 8 hours. So if you have two 300 amp hour, then this becomes 16. And if you have three of these 300 amp hour, then it can become 24 hours. Yeah. So yeah. And if you got lots of batteries, you could go as 48 hours or 32 hours, that sort of thing. So just availability of budgets. That is, what are you willing to budget? What's your critical needs? I hope that a person can decide, well, this is important to me. I want more battery. Okay, that's good. Or you could say, well, based from this sort of explanation, I want more solar. That's good too. There's no good or bad. I mean, there is there isn't really a bad or good thing about this sort of analysis. It's more about needs and wants, and hopefully this can explain the overall requirement of running a house like that. Right now, without the aircon and 5 fans running, it's consuming around 200 watts. And if you're running it for 1 hour, it's 100 watt hour. So multiply that over 24 times 30 days. That's your energy use. So yeah, that's how you calculate things. It's now 9:39, so the load is that. And let's see here. Then the battery is 25.2. It's 11:30, and the unit is powered down. There's no output, so the voltage is 24. Just gonna turn up the AC. Okay, so I'm going to turn on the panel, turn off the AC, and plug in the meter, turn on AC to charge the battery. So input 245. It's gonna want to charge the battery. I think okay, so it's charging. Solar and AC is charging the battery. So it's at 51 amps. Like I showed before, BMS sets the charging current to 50, so, or less than 50. So it's let's see how long it'll charge. I have to find out the real time with my son. I have to go to Roxas. We just got back. So I started at 8, and the inverter the battery lasted till 10:48, 10 o'clock 48, which is 2 hours 48 minutes, which is one of my calculation here, 2 hour 44 minutes. So that's it. It didn't last 3 hours 18 minutes, nor did it last 3 hours 12 minutes. It came close to this calculation, 2 hours 44 minutes, with this kind of uh, draw. So 887 watts or 850 watts. So basically calculation according to power power draw come close to the actual time that it lasted. So yeah, here you go. I'll do some more math. It's now 12:30, so let's do some calculation for what if. Okay, suppose we need the inverter to be running for 24 hours because typhoon came in, and we need to have power for 24 hours. Suppose typhoon typhoon and need energy for 24 hours. Okay. Okay. Suppose we can only afford 24 volts 100 amp hour. Okay. Or we budget for a battery that is 24 volt 100 amp hour. How many batteries do we need? So 24 hours, so we need let's see, this 24 volts times 100 is 2400 watt hour. Okay. Suppose power consumption is 100 watt 1000 watt. Okay, so that's what the power consumption is, 1000 watt for the typhoon and whatever. So, and we need 1000 watt running for 24 hours. So 24 hours. So to continue, I was interrupted. So we need to run for 24 hours this 1000 watt. So calculating 24 times 1000 is 24,000 watt hour. Okay, so now one battery is 2400 watt hour. So basically how many batteries will this be? So how many bat is 24,000 watt hour? Then we just say 24 divided by 2400, so that's cancel out to 1. Okay, so that cancel out 2, so what's left is 1 0. So we need 10 battery. Okay, so you need these batteries, 10 of these, 1 all the way to 10. That's it. That's how you do this calculation. Fairly simple. Now if you can buy let's say you can buy 24 volts 300 amp hour, well then just divide by 3, so you need 3.5, or just basically 9 batteries, no, 3 batteries. Okay, so 3 of these, there's 100, 100, 100, so 10 divided by 3, so you have 3 batteries, that is 300 amp hour. So now if you can buy 400 amp hour, then you only need 2.5 or just 2. Basically that's the what if. Yeah, okay, hopefully this lessons is pretty good. some understanding is needed. Hopefully it's maybe confusing or clears up any of these requirements that you have been thinking about. Thanks for watching.